Thank you. So my thanks to the organisers who are mainly not here, but especially to Katerina who had the decency to turn up. Yeah, so this is joint work with many people. So there's Armin who's here, Armin Tagavi-Shabir, and Daniel Snell, who was a student of mine. And then, so that was the first bit that I'll talk about. And then more recently, it was a sort of follow-up to that, dealing with submanifolds, which is with Sean Curry and Daniel Snell, again, which is the item on the archive there. Okay, so let me start with the story. So first of all, we'll talk about sort of one manifold, so curves. So this part, I hope there'll be aspects that sort of feel familiar to a lot of people here, and it sort of suggests how the whole thing goes. So here's the sort of motivational problem, if you like. So it's not what the whole talk is about, but it's a sort of a real problem, and so gives you a sort of suggestion of how to attack something in a way where you want to get actual results for that thing. So the problem is to construct what are called first integrals, and we'll just remember the classical story of this. So on a pseudo-Riemannian manifold now. Most of the talk I'm going to restrict to Riemannian signature. It's not that it doesn't work in other signatures. It's just that you have to say a lot of extra words all the time. So mainly we'll stick to Riemannian signature. But anyway, in a Riemannian or pseudo-Riemannian case, a geodesic. So we'll understand it as a curve that is sort of auto-parallel in this sense. So its velocity is parallel along the curve, right? So the usual thing. So here U is the velocity of the curve, and now let's say the Levi-Civita connection. Now, it's well known classically, and I'm sure most of you have heard of that it's useful when you're studying such things to find what are called first integrals. So these are quantities that are conserved along the curve, necessarily conserved if it's a geodesic. And the idea is that, maybe if you have enough of these conserved quantities, then you could algebraically find the geodesic, or if you don't have quite so many, it at least simplifies the equation of finding the geodesic. So the easy way to construct these is if you start with a killing tensor. So killing tensors are things that, if you like, generalize killing vectors. So the killing tensor here is going to be a rank L symmetric tensor. And then you take its covariant derivative and take the symmetric part of that. If that's 0, then that's what we call a killing tensor. So for a killing vector, of course, it means the Lie derivative of the metric along the vector 0, and it boils down to this equation, where in that case you're in rank 1 for the tensor. Okay, but suppose we have such a killing tensor, then this gives a first integral for geodesics. How do you see that? Well, you just saturate this tensor with by contracting in the velocity as many times as you can. So you get a function along the curve. There it is written in indices. And this has to be constant along the curve if it's a geodesic. Okay, why is that? Well, let's just differentiate it in the direction of the velocity. So we're differentiating this function in the direction of the velocity. And now you use the Leibniz rule, either it hits K, and you can use the covariant derivative in your Leibniz rule. So it either hits K, in which case, these U's are going to symmetrize it, and so it vanishes because it's a killing tensor, or the U hits the U in the Leibniz rule, and it's 0 because of the geodesic equation. So it's sort of visually obvious that this is a conserved quantity along the curve. All right. In fact, this is part of a more general story. This works for any affine connection. In fact, there's a sort of projectively invariant part of this story, but I won't be doing that today, but just to say that there is a path you can go down there. What's that? There is a projective story behind it. Yeah. So there's So this geodesic equation, if you put weights in, it becomes projectively invariant. And then yes, you can. What's that? What? You use a weighted U, and then this all just works. But this is why I said I didn't want to do it now, because I can explain it to you afterwards. But yeah, there is a projective version. Okay. So let's go to conformal geometry now. So what does a conformal geometry mean? Well, hopefully everyone knows here, but perhaps not. So a conformal manifold is just a manifold equipped with an equivalence class of metrics. So where the metrics related by multiplying by a positive function. So this is an equivalence relation, of course. Where G hat's related to G by multiplying by a smooth positive function, we say they're conformally related. A conformal manifold is just a manifold equipped with such a conformal equivalence class of metrics. So when you only have an equivalence class of metrics, of course, the geodesic equation is not conformally invariant unless it's a null geodesic. If we restrict to Riemannian signature, then the geodesic equation is just not conformally invariant. So what are sort of replacement distinguished curves? Well, the sort of, if you like, lowest order analog of a geodesic are these things called conformal circles. So here's a conformal circle equation. So this is an equation for a curve, which is now higher order. So A is the acceleration, U remembers the velocity, and we're getting other items involved. So this is the Scouten tensor, which is a trace adjustment of the Ricci tensor. And this dot just means U contracted with itself and so on. So it's an obvious notation. But anyway, the main point is here that the equation's slightly complicated. It's a natural equation, and it describes the distinguished curves on a conformal manifold. This is a sort of parametrized version. So this is due to Jarno and I guess due to Jarno and also studied by Scouten. And it's conformally invariant. So this gives you well-defined equation on a conformal manifold. You have to specify to determine a curve, you have to specify at a point, well, the point you're at, then the velocity at that point and the acceleration at that point. Yep. Pardon? Gamma dot dot. Oh, the second derivative of the dot is the velocity. What's that? Yes. Covariant derivative, yeah. Well, it's a covariant derivative, yeah. So. Okay. Yeah, that's a common notation, but it's a dot and then a covariant derivative. Okay. So it's the acceleration is the covariant derivative of the velocity. So along the curve. So this equation is conformally invariant. It's third order and complicated. So how would you find first integrals for that? So you can't now just mimic the last thing, right? Because somehow the equation is quite complicated. So this is what I mean by a motivating problem, right? So now some examples prior to our work were due to, so Todd and also some Japanese people had written down some first integrals, but there wasn't a sort of conceptual approach. So I want to think of that as a motivating problem for studying both the geodesic equation, but then also finally submanifolds, and I'll come to that. Okay, so conformal geometry, my usual mantra. So in a conformal manifold without further restrictions, there's no distinguished connection on the tangent bundle, but there is on this bundle of slightly higher rank, right? So there's a rank 2 extension of the tangent bundle or cotangent bundle. Here, this notation means the cotangent bundle tensor product a line bundle, which has what we call conformal weight 1. This is a root of the canonical bundle, and there's the formula for it. You take the top exterior pair of the tangent bundle, square it to make it oriented, take that root, that's that line bundle of weight 1. And then if you took, this tensor itself, it would have weight 2 then, and so on. So there's an obvious weight counting. Okay, so So this thing gets called the conformal tractor bundle. And why it's important is that it has a conformally invariant connection on it. So, so when you pick a metric from the conformal class, this bundle decomposes into a direct sum of these two line bundles with the cotangent bundle. Up here, this is a sort of improvised notation, if you like, for a semi-direct sum, meaning that that this this bundle is a sub-bundle of the tractor bundle. And then this bundle is a quotient of the bundle, and so on. But when you pick a metric, it just decomposes into a direct sum like that. So then a section of this bundle can be written as a triple, sigma from the densities here, rho from the densities there, and your cotangent with some weight. And the formula for the tractor connection is here. The details don't matter. The main thing is it's a pretty simple formula, So here's the Levi-Civita connection leading this at each slot. There's a bit of the Scouten tensor coming in, and so on. So an algebraic modification, if you like, of the sort of obvious use of the Levi-Civita connection on there. Okay, so the point is that this is conformally invariant with you as written, you need to interpret what that means, but it is genuinely a conformally invariant connection on this bundle. And what's more, it preserves a metric. So here's the metric given as a quadratic form. You can see from that it's got Lorentzian signature if the original manifold if the original underlying manifolds were Riemannian. So then we'll write a notation. So we won't have to use this that much, but sometimes we will. So this triple sigma mu rho can be written as sigma y and then mu contracted into z and then rho times x, where these are the, if you like, the algebraic maps, the bundle maps that are putting you in those slots. Any questions about that? Okay. Now, just one thing that's very important. So I've mentioned those three things. One of them is conformally invariant. So this x, if you like, so this is conformally invariant. So let me go back. So in this triple, so the y and the z change when you change the splitting by picking a different metric from the conformal class, but the x itself is invariant, and it's a very fundamental object. So from this point of view, it gives you the filtration of the tractor bundle, and it has information about your position on the manifold. So I won't go into detail into that, but if you want to talk about it later, I can. So, so just bear in mind that that's a sort of canonical object. Okay, so now what is a conformal circle from this point of view? So, so suppose you have some curve and you want to ask, is this a conformal circle? You're on a conformal manifold. So the answer is, well, an answer is that it's a conformal circle if along this curve you have some parallel tractor. So what am I calling it here? Star n. Okay, and it's got three tractor indices. So A1, A2, A3 or something. And it's skew on those three. So it's a three tractor. And it's parallel along the curve. Of course, it's easy to make something like that parallel along the curve. Just pick one at a point and parallelly transport it. But the other bit of information is that we're going to ask that it's incident with x, right? So when you wedge this canonical tractor with it, you get 0. And if that happens, it's a conformal circle, just like that, right? So it's an incidence relation. So parallel things along here are not unique at all, but if they happen to be incident with x, then that's a conformal circle. No, it's anti-parallel. It's the opposite. Yeah. So x is very much not parallel. That's why there's a lot of content when you ask it to go in there. As I say, x defines the filtration. You'll see shortly in the model where this all comes from. Okay, so here's a sort of brief sketch of the proof. So first of all, let me check how slow I'm going. 245. Yeah, it's okay. Okay, so an unparameterized conformal circle. So I gave you the first equation for a conformal circle, which was the formula for a parameterized one, because I wanted to make it look as complicated as possible. it simplifies slightly if you work with unparameterized conformal circles. So then you can use a unit length velocity with a weight, right? So u is a velocity vector, but it has a weight. If it's a contravariant, it has weight -1. So you could think of that as the usual velocity, but divided by its length. And then you form a weighted acceleration. So again, this is a covariant derivative along the velocity in the direction, along the curve in the direction of the velocity. You differentiate the velocity, but you're using this weighted velocity. So this is a covariant. This is a sort of, it's not quite the usual acceleration, and it's not just the weighting of the usual acceleration, but it simplifies this equation. Okay, so that's the first thing. So that's an unparameterized conformal circle. If you have that, yeah. This just makes it unique, right? So you have a curve, you pick a tangent along the curve, and then you make it unique. It has that weight by asking it to have length 1. That's the way to think of it. No, because it has a weight. No, because it has a weight. Yeah, yeah. If you start with an unweighted one and divide it by length, then you get this weight and you have no parameterization. Right? It's the other two ways of saying it. Yeah, so this is unparameterized. Okay, so is everyone else clear on that? So you just, you take this u to be in the direction of the curve, so it's a tangent vector along the curve, but give it weight -1, and then make it unique. There's an orientation with this thing, so there's an arrow on it, so there is a direction. But you make it unique by making it have then length 1, and it's then unparameterized.
Parameter is such that velocity has length 1.
It's yes, essentially the same. Yeah, but we're working with weights, and we want to think of it that way. Yeah. What's that? Yeah. This. It doesn't. You're dividing by the. Yeah. Again. Yeah. Yeah. That's right. It's an unparameterized curve, and this is the way of doing it. Anyway, these are sort of details. So what isn't a detail is to use this weighted acceleration, because as I say, it's not just the reweighting of the not usual acceleration, but it's the derivative along the curve of this. Then it simplifies. Okay. So that's one fact. Then you can form this conformally invariant object. So starting with your curve, so just any curve, it doesn't have to be a conformal circle. You can form this thing that's a bit like a splitting operator, but non-linear, right? So here's the velocity, here's the acceleration with the velocity, in fact, sort of wedged because this is skew. And here are these tractor projectors, right? So this is putting them into tractors, that information. This is a conformally invariant 3 tractor that you can make along any curve. Okay, why not? Then, using the formula for the tractor connection, you see that the equation of parallel transport for that is exactly this equation up here. So it's an unparameterized geodesic if and only if this is parallel, right? When I say unparameterized, they're always directed. They have an orientation, but I won't say that all the time. Okay, so that's the second fact, and that's already a theorem in a sense. So this is one way of describing conformal circles, that you take this conformally invariant object that you can associate canonically to your curve, and it's parallel if and only if it's a conformal circle. So it's really a separate theorem, but it is the theorem I stated needs this next bullet point. So observe that if you have this thing, so if you have a 3 tractor that takes this form, then it satisfies the incidence relation of wedging with x of 0, because look, there's an x in those 2 things, right? So that gets killed. So that does the theorem in one direction, because if it's a conformal circle, you have this and the wedge is 0. In the other direction, suppose you just have a parallel 3 tractor and X wedge that's 0, then actually the parallel thing has to look like that. And that's easy because you just start differentiating this thing along the curve. It turns this X into what's called sometimes the velocity tractor. You differentiate again. It turns into a thing called the acceleration tractor. And then you put that information together and you see that that's what you've got. Okay, so as a little payoff now, we see that you can now, at least in some circumstances, proliferate conformal conserved quantities along the curve, so first integral. So how do you do that? So take any, so suppose this is a conformal circle, then it has this parallel 3 tractor. Yeah. So if you have lying around some other tractors with, and you can somehow pair them with those 3 indices, or perhaps several copies of that, you may take 3 copies of that and 2 of these tractors, but you can contract it together and make a scalar. And if this is parallel, then the object is going to be constant along the curve. Yeah. So that's what this is all saying. So you have some psi, which is a parallel tractor, but it may be made of simpler parallel tractors. And you compare it with tensor products of this canonical object in such a way to make a scalar, then that's going to give you first integrals along the curve. That's it, right? So so now it sounds like you're doing nothing, but actually, when you do the projective version of this recovers the usual way people make conserved quantities for geodesics. So using Killing tensors, using Killing-Yano tensors, and so on. So that's they're a sort of special case of this idea. Well, there's some fine print, and I'll come to that. So this, you can get from this immediately sort of everything people know about first integrals for geodesics and so on. But then this is doing exactly an analogous thing that does it for conformal circles as well. Now, the important thing here is that, well, an important thing is that it's not only Killing tensors and Killing-Yano tensors. So as those of you who know some tractor things around here will know, so if you have any first BGG equation, then its prolongation yields a tractor. And if that tractor is parallel, then that's what we call a normal solution of that BGG equation. So anytime you have normal solutions of BGG equations, you can somehow form a scalar like this, then you get a conserved quantity. So you don't have to start with your favorite Killing objects and so on. Okay, let's look at how it works in practice. So here's an example for conformal circles. This is like the simplest one. So suppose you're on a manifold equipped with a parallel 3 tractor. That would be useful, wouldn't it? Because we have an object with 3 indices. So suppose you have a parallel 3 tractor on your manifold. Then you can just contract this object that we have along curves into that 3 tractor. And if the curve's a conformal circle, then the star n thing will be parallel. The k by assumption is parallel, so you'll get a conserved quantity. What do parallel 3 tractors have to do with the meaning of life? Well, they're linked to Killing-Yano tensors. So the parallel 3 tractor has a bunch of slots. Well, it has like 4 slots. And the top slot will be a rank 2 skew tensor of conformal weight 3. And those are the weights I was talking about before. And it'll satisfy this Killing-Yano equation. So that's what I've written here explicitly. That says that the derivative of this rank 2 tensor consists of a part that's completely skew and a part that is trace, and that's all, right? So some of the irreducible parts are missing. And so that's the Killing-Yano equation. It's an overdetermined PDE. So the prolongation of that arises, if you like, by using one of these BGG splitting operators. So there's a thing that will take one of these tensors of that weight and turn it into a 3 tractor. It's a differential operator that's a splitting operator. In other words, it has a algebraic inverse. And that's what you contract into this parallel object along the curve. Now, the theorem here says that in fact, this K doesn't need to be parallel. You only need, it turns out, you only need this K to solve this Kiliano equation. You make this BGG splitting operator and form this object, and that's what you get here. And that is a conserved quantity along the curve. And although this is not parallel, it's nearly parallel for the tractor connection, and that's why it works. But I won't go into that detail. Okay, so here's the first, what I'm calling looking under the bonnet. So, yeah, so Kiliano, that's what I've already said. So when you form this prolongation, it looks like this, right? So this is the BGG splitting operator. Here's your Kiliano tensor. Here's more or less its exterior derivative. Here's its divergence, and there's some second order operator on the bottom that I'm not, I don't care about. Now contract this with the star n. What does the star n look like in slots? So these, this is the tractor written in slots. So this bit is skew tensors at the top. These are rank 1 things here, rank 3 things, and so on, and 2 tensors down here. So the star n really is just 0, 0, the velocity, and the velocity wedged with the acceleration. So it's actually very simple. And you're contracting it into that. Well, this slot contracts into the top. This vector contracts into that divergence of k, and that's where you get that from. So it's not very hard to actually write that down. Okay, so we've constructed our first integral. Now, anyway, so you can go on and make other examples, and if you want to see some more later on, I've got some after the end of the slides. Let me talk about looking under the bonnet in the other way. Where did this, this version of understanding conformal geodesics come from in the way I'm telling you about them, right? So here's the model for conformal geometry first, right? So take Rn plus 2. Everyone's happy with that. Equip it with a Lorentzian signature metric. Okay, so it's just Rn plus 2 with a Lorentzian dot product. So then you get a quadric, right? So you get the null quadric of this bilinear form. So there I've written my shaky cone. That's the null quadric. Now, if you take a ray projectivization of that quadric, let's say just take the forward part of the cone, if you like, take the ray projectivization, then you get a sphere, right? That's sort of obvious, but it is equipped with a conformal structure. That's less obvious. But this is the standard model of the flat conformal sphere, we call it. So it's the sphere with a conformal structure. It's the ray projectivization of this cone. So, and the way you see that is if you take a section, you get a section of the cone, and then that gets induced on a metric from this one. And if you change your mind about the section, you get a conformally related metric. So that's how you see it. And it's easy to see by taking a section, suitable section, that you get the round metric. Okay, so that's the sort of key tool for sort of a first foray into conformal geometry. You should always understand this model. And then, okay, now, suppose you want to make some distinguished submanifolds on the sphere. What's the most obvious thing to do? You're sort of threatening to slap your student, and you say, go and make me some distinguished submanifolds on the sphere. And so what they'll almost certainly do is go away and take some sort of plane through the origin and intersect it with that cone. And when you take the ray projectivization, it'll produce nice submanifolds here, right? So if you take a dimension m plus 2 plane through the origin and do this, then you lose the intersections dimension m plus 1. The ray projectivization gives you something of dimension m here, yeah? And this is just a totally geodesic subsphere. And that's how they arise on the sphere, right? So leave that as an exercise. So all these totally geodesic subspheres arise from intersections like this. Okay, so that's what we think of as nice submanifolds. Sorry, totally, did I say geodesic? Totally umbilic is what I meant to say. Totally umbilic subspheres. The totally geodesic would have to be, well, this is a conformal structure, so it doesn't really make sense. But on a round sphere, the totally geodesic ones, of course, are the spheres that share the origin with the original sphere. Okay, so how did you specify this plane? Well, of course, the obvious thing to do is to give a spanning set of m+2 vectors, but then of course you're giving too much information, so you wedge them together and make an m+2 form, right? So a vector which is completely skew and has m+2 indices, and that's how you, but simple, that's how you specify such a plane. That's the parallel tractor. And the incidence is the incidence, to say that the x becomes the homogeneous coordinates here, and the incidence is that it lies in the plane, right? So that's where it's coming from. And in a sense, the story I just told you is that works in the curve setting, right? So the tractors sort of promote that to the curve setting and give you a nice way of doing things so that you can then do things like construct conserved quantities. Okay, so that model then suggests that we should also look at doing this for submanifolds, because that was talking about curves. But now the idea is that this story will generalize. So as I say, part of the story is making conserved quantities, but that's a sort of a proof of concept in a way, because the idea really is to develop a good conformal submanifold calculus that is useful for applications, including that, but lots of applications. Okay, so any questions before I go on? Yeah. They're okay. In the way I'm presenting them, they're in a different category. So for null GD6, you use a 2-tractor, not a 3-tractor. But so they're like a separate class of curves in the way I'm presenting it. No. It's not as far as I know, but it won't happen, I think. So, okay, so now let's look instead at conformal submanifolds. So, perhaps I use the same picture. Now this will be a submanifold of dimension m, right? So we will think of just submanifolds embedded in conformal manifolds. Okay, so the m, all I want is that it's proper in the dimensional sense. So, okay, now along a conformal submanifold, the ambient tangent bundle splits into the tangent bundle to the submanifold. And of course, because you have a conformal structure, you know what orthogonal means. So you get a direct orthogonal decomposition into the tangent bundle and what's called the normal bundle. Okay, this is the sort of basics of submanifolds. Now, we would like a tractor version of that. So for each metric in the conformal class, you can make this mapping, but this is actually turns out to be conformally invariant. So here I take any normal vector to my submanifold, and I map it into a tractor. Remember, the tractors were triples. I put 0 in the top slot, I put the normal thing in the middle, and then I contract it with the mean curvature. If this is an arbitrary submanifold of some codimension, then the mean curvature is vector valued normally, right? So the mean curvature is a vector determined by a metric in the conformal class here. But then when you change your mind about the metric in the conformal class, the mean curvature is not conformally invariant, but it's not conformally invariant in exactly the right way, so that this transforms in the way tractors should transform. So this map is conformally invariant. So it determines an isomorphism from, in fact, you use weight slightly, so that the normal bundle twisted with densities of weight -1 is mapped onto its image in the tractor bundle. This should be restricted to sigma, along sigma. And you just define this curly n to be the image of this map. Okay, so it's a sub-bundle of the tractor bundle. So we have a sub-bundle of the tractor bundle, but remember, we also have a tractor metric. And so you can orthogonally decompose into that sub-bundle plus what's left. Right, so the n perp. But then there's a theorem that the n perp is actually isomorphic to the intrinsic tractor bundle of your submanifold. So here we're in a conformal manifold, And so by restricting each metric from the conformal class to the tangent vectors here, you get induced on the submanifold a conformal structure of its own. Right, so that submanifold then has its own tractor bundle and tractor connection and so on, unless of course you're in low dimensions. So Boris would surely say, but what about low dimensions? But then you get induced on a Möbius structure, a distinguished Möbius structure by the embedding, and so you still get tractor bundles, what we'd call intrinsic tractor bundles for those things. So it turns out that actually the ambient tractor bundle along the submanifold decomposes, that's rain by the way, orthogonally into this normal tractor bundle and the intrinsic tractor bundle of the submanifold. So I'll write pi for the projection either from the ambient tractor bundle onto this tangent tractor bundle, if you like, and this n will be the projection onto the normal tractor bundle. Okay, now everything is conformally invariant, and so you can start to mimic in a conformally invariant way what you would do with ordinary submanifold theory and Riemannian geometry. So this is based on sort of work over a number of years, really, with my students, and especially most recently Sean Curry. But the first thing you can do is to find what we call the check connection along the submanifold, which means you take the ambient tractor connection, apply it to tractor, tangential tractors, if you like, by putting those in the ambient tractor bundle using this pi, then you differentiate and then you project back, the sort of obvious thing that you do with projected connections. So that gives you a connection on the tangent tractor bundle to your submanifold. And then that differs from the ambient connection because it was projected in by a normal part. And that's how you define the tractor second fundamental form. So it's analogous to the way the second fundamental form is defined in Riemannian geometry. So the difference, so you take like a tangential tractor, if you like, so living in that bundle, differentiate it with the ambient tractor connection, then here's the checked one, and then the difference is this thing here. And then this gives the tractor Gauss formula. You can also compare the check connection. So here we're comparing it to the ambient connection. You can compare it to the intrinsic tractor connection. So remember, this has its own conformal structure. So it has its own intrinsic tractor connection. And what's the difference between that and this check connection? So I'm writing this D for the intrinsic tractor connection. So it differs by some contortion object. The contortion object, so these X and Z are just these tractor inserter things. So the difference really boils down to this Fialkov tensor. So this is a tensor first due to Fialkov that's conformally invariant. And it's really a difference. The main thing here is the difference between the Scouten tensors. So this is the Scouten tensor for the intrinsic submanifold metric, the one that's induced on the submanifold. Here's the ambient Scouten tensor, but restricted to the tangential directions. And that's the leading part of the Fialkov tensor. And the second fundamental form and the mean curvature are entering as well. Okay, so these are objects that emerge. How does the tractor second fundamental form look in details? So here it is. It involves the usual second fundamental form, the ambient Scouten tensor with tangential and normal indices and so on, the mean curvature and so on. Now I want to introduce a definition. So I talked about distinguished submanifolds in the sphere. So let me say that a submanifold generally is distinguished if L equals 0. So if this tractor second fundamental form is 0, why not? Now, if you're on the sphere, this boils down to it just being totally umbilic. But in general, it's more than that. So it's totally umbilic, and this other invariant due to Belgin has to also vanish, which is essentially this next slot in the tractor with a little modification, right? So distinguished is going to mean this L is 0. So why am I making this definition? Well, one application of this is to study what it means for a submanifold to be totally conformally circular. So here we have weakly conformally circular. So what it would mean for this to be weakly conformally circular is that if you start off with a point on the submanifold and a tangent vector to that, and another tangent vector that's going to be the acceleration, but all tangent to the submanifold, but then you use the ambient conformal circle equation, does that curve stay in the submanifold or not? If it stays in, then you say it's weakly conformally circular. Okay, so now the theorem here, which is a corollary of all this stuff, is that the submanifold's weakly conformally circular if and only if it's distinguished. So in other words, if this L is 0. Yeah, and that's just what I was. Pardon? So you don't. It's a longish proof, but it's much simpler than in Belgin. So Belgin did a version of this, not using tractors, that has some very nice aspects, but it's very hard to follow. But in this direction, if L is 0, and this bit is very much inspired by what Belgin did, you define a family of curves which solve a third-order equation that looks a lot like the conformal circle equation, but has the property that it defines curves that lie in the submanifold. So it's made out of things that mean that the curves stay in there, and then the equation is constructed in such a way that you can then show that if L equals 0, that actually those curves are conformal circles for the ambient conformal structure. So it's a slightly subtle and quite complicated argument. So I can't give it all here, but that's the idea. In the other direction, it's now easy using the technology I've already mentioned, because each conformal circle determines one of these parallel 3 tractor objects. Yeah. And so those things, each of these is tangent to the curve that you want to lie in here, and orthogonal to the normal projector, the tractor normal projector for the submanifold. And so if all of the conformal circles stay in the submanifold, you have lots and lots of these parallel things around, and they just kill off. They force this projector to be parallel, and therefore L to be 0. So in that direction, it's really, now quite simple. Anyway, so I won't give the proof of this, but it's not hard to show that the submanifold strongly conformally circular exactly if L equals 0 and the S is 0. In other words, the Fialkov also vanishes. So strongly conformally circular means that the conformal circles of the intrinsic geometry here exactly agree with the conformal circles of the ambient geometry. So there's the 2 different notions. Okay, so tractor normal forms. Okay, so I want to talk about another way of sort of doing this submanifold calculus that turns out to be very useful and important. So far we sort of proceeded in the usual way, which is to make these projectors and a normal projector and a tangential projector, but in the tractor sense. There's another thing you can do, and that is make these forms, right? So for a submanifold of codimension D, right? So I was saying they had dimension M, but let's say that's codimension D, then the top exterior power of the normal bundle or the dual normal bundle is obviously a line bundle, right? Because it's got rank D. So N has rank D, or N star has rank D, so its top exterior power is the D power. So that's a line bundle. The tractor version of the normal bundle has the same rank as the normal bundle. Remember, that was an isomorphism. So the top exterior power is also a line bundle. Okay, now, so these have these canonical objects. So there's unique, that's what I mean here, compatible with orientation, normal D form. So this is a section of the top exterior power of the conormal bundle, but with weight D. And the weight D means that you can, when you contract it with itself like this, then you get something of weight 0. So you can normalize it so that this length is d factorial. Okay, so it's just a way of normalizing it. So this is uniquely determined by the submanifold. And then you can make a tractor version of it basically by you make a d-tractor, so it has skew d indices by putting this, you put zeros over here and you put this thing in what we call the west slot, right? So this is using all those z injectors. And then in the bottom slot, you put that contracted into the mean curvature. Anyway, the details don't matter. It's an obvious way of making a tractor version of that normal object. And then the other thing you can do, since you're playing a mathematician and you're playing around, is you can take the Hodge star of this thing. So you have a tractor volume form. So in conformal tractor calculus, there's a tractor volume form. So it would have, if you're in dimension n, it would have n plus 1 indices. N plus 2 indices. So you can do sort of Hodge starring in the usual way, but on tractor indices. So you can convert this D form into a M plus 2 form with this by contracting in. Okay, now this one clearly satisfies an incidence relation in the sense that X contracted into it is 0. That's what these two zeros mean, basically. Yeah. So these two zeros mean that it must be that X contracted into that is 0. And when you Hodge star it, it means that X wedged, the Hodge star version, will be 0. That's the usual gymnastics of Hodge stars. Okay, so using these, we can talk about distinguished in now many ways. So remember, a submanifold is said to be distinguished if this tractor second fundamental form is 0. Right? Now, the claim is that that's equivalent to this normal projector being parallel. I could have also put that the tangential tractor projector would be parallel as well. It's equivalent to this first type of normal form being parallel, or it's Hodge star being parallel. So they're all ways of saying that it's distinguished. So what's the proof? Well, it again is a little bit involved, but the idea is simple. So the tractor second fundamental form, it's not hard to show. It can be written in this way. So you differentiate this normal projector and then contract in the normal projector to project it back. So that C is a normal index. So, so that being 0 means distinguished by definition. It's clear that 2 implies 1 then, right, from this formula, and it's not so hard to go back. Then to see the link to these other ones, it's the observation that if you take these normal forms and contract like that one, and contract it with itself in the right way, you get the normal projector back. Yeah, so some stuff. Okay, so now we have, we can make first integrals for these distinguished submanifolds in exactly the same way. So normal BGG solutions give submanifold first integrals. Why is that? Well, just the same argument. So if you have a first BGG solution that's normal, then it produces a parallel tractor. And so if you can somehow contract such parallel tractor or tensor powers thereof into any one of these objects or tensor powers thereof, then you get something that has to be parallel along the curve. So you can proliferate conserved quantities for these things when you have normal solutions, right? So here's an example. I probably won't go too slow. It's not actually the same as the one before, but it looks very similar. So again, we start with the Kilignano tensor, but now it's instead of just a rank 2, let's take a rank D Kilignano tensor. So that's skew with D maybe D minus 1, in fact, this time. And so its derivative is completely skew or has a trace part. That's the Kilignano equation. That prolongs to a tractor that is completely skew and has D indices. And so you can contract it into one of those normal objects that has to be parallel if the submanifold's distinguished. And so you get a conserved quantity. And so the only thing, if it's a normal solution, everything's parallel, so that's obviously constant. and you only need to check that it's non-trivial, and you just expand out what it is, and it's non-trivial in general. Okay. Now, I just wanted to finish this part with an alternative characterization of distinguished submanifolds. So remember back when I did distinguished curves, it wasn't by saying that some second fundamental form was zero, although we could now do that, but it was by the existence of a parallel object. Well, that works again. So if you have a submanifold, then it's distinguished if there's anything along there. So this is a skew detractor that's parallel along your submanifold and is incident in the sense that when X is contracted into it, it gives 0. D is the codimension. So yeah, if this is parallel and incident, then it's distinguished. And then you can do the Hodge-Star version. So if you have an M+2 tractor that's skew and it's parallel and incident in the other way, that X widget, then it has to be distinguished. And the proof in the one direction is you just take psi to be that normal thing that I just talked about how to construct. To do the other one, you do the Hodge-Star. And then just as in the case of curves, it's easy to show that if it's parallel and you have the incident relation, then you actually get that normal splitting operator that I had written down that we use. Okay, so a corollary is that conformal circles are, of course, distinguished one manifolds. They fit into this theory just as the one-dimensional thing. So the other way of saying the conformal circle equation is that the tractor second fundamental form vanishes. So for the one manifold. It sounds strange for a curve, but yeah. Okay, there's a story about zero locus. So this is another corollary. So this is a corollary of this previous page, right? So when you understand the distinguished objects this way, then you can make these sort of conclusions. So if you suppose you have a normal solution of the Killing-Form equation, that's just the Killing-Yarnow equation, conformal Killing-Yarnow equation, sorry, such that it's simple, right? So that the tractor, the prolongation to a tractor has to be simple, then the zero locus of not just the solution, but its solution and its divergence, right? So those both have to be 0. So this is either empty or it's a distinguished conformal submanifold of codimension D. So how do you see that? Well, because it's a normal solution, when you take this BGG splitting operator on K, you get a detractor, which is then parallel. And this zero locus of these two things is exactly this incidence relation. So you now have a parallel detractor satisfying the incidence relation. So you're nearly done by the previous things. The only thing you need to apply the previous theory page is to know that the dimension of the zero locus is actually of the right dimension. So it's dimension M. And you can either, there's an analytic way to see that from this, or a simpler way is to use this curved orbit theory that we use. So in the model, it works to have the same dimension, and this is a p-type statement more generally, so you know it has the right dimension from this work with Andy and Hammerall on Cartan holonomy. Okay, so I just want to finish quickly with a little story about yes, a few minutes. About things like the mean curvature. So the mean curvature, of course, is, you might think, well, what's that got to do with conformal geometry? Because it's not conformally invariant. But of course, people are very interested in studying, minimal submanifolds, CMC manifolds, and so on. So it's interesting to understand how that's described in this way. And it's actually useful because let me tell you the sort of motivation. So one of the things that people want to study are conformally compact manifolds. So you have a manifold with boundary, and on the interior you have some, maybe it's M bar is the manifold with boundary, and on the interior you have a metric, let's call it G plus or something, that's complete. Then then this is conformally compact. If there's a metric, let's say G, which is so R squared times G plus, where R is a defining function. For the boundary. Okay, so R being a defining function for the boundary means that the boundary is the zero locus of R, and D of R is nowhere vanishing along the boundary, right? So, and this metric G, is smooth to the boundary. So this extends as a metric, extends to the boundary of M. So it's really a metric on the whole of M bar, just a smooth metric. That's what I mean. So then we would say that G bar plus is conformally compact. And so what people are often interested in is studying things like minimal submanifolds that go out and meet the conformal infinity, right? So then you want some sort of more advanced notion of what minimal means, because you want to understand it where you're going to where the metric. It's minimal for the metric G plus, but G plus is not defined at the boundary. So you want a tool for understanding such things. Okay, so what's minimal? So so a very useful thing in conformal geometry when you want to work with an actual metric is this thing called the scale tractor. So here's the conformal metric. So conformal manifolds have a thing called the conformal metric. And then metrics from the conformal class arise as sigma to the -2 times the conformal metric, where sigma is a density of weight 1. Okay, so there's a few things if you're not familiar with, I could explain to you later. But anyway, so metrics from the conformal class correspond to such sigmas. And then given such a density, you can form this tractor by taking sigma, its derivative, and then this sort of Laplacian thing. So that gives the triple. So this is what we call the scale tractor. And it's the object that's breaking the conformal invariance sort of at a bundle level. Okay. And I'll call this sort of thing a scale tractor, provided sigma's nowhere vanishing on an open dense set. All right. So now, given a submanifold, if you have a metric, then you get a mean curvature, and you can turn it into a tractor by using this NA thing we wrote before. So this was the thing that gave the isomorphism between the normal bundle and the tractor version of the normal bundle. So you can put the mean curvature into a tractor like that and call that the tractor mean curvature. So it has the same information as the mean curvature. Then the key observation is that this tractor mean curvature is given by this normal projector, tractor normal projector, contracted into the scale tractor. Okay, now, when you're looking at it like this, you think that this is just written another formula, right? So what do you get out of it? But look at what that's saying. That's saying that the submanifold, for instance, is minimal exactly if the scale tractor is orthogonal to this normal tractor projector. In other words, it's minimal if the scale tractor is a tangent tractor to your submanifold, which is a very nice geometric condition. And in particular, it enables you in situations like this to go, because everything here, once you have this notion, they extend to the boundary. And what you see, for instance, is that it's easy to see from this conclusion down here that if you have a minimal submanifold, then it has to meet the boundary orthogonally. So it's basically coming from this condition, because let's say this is a Poincaré-Einstein manifold, meaning it doesn't need to be so strong, but let's say it's Poincaré-Einstein, meaning that it's actually an Einstein metric on the inside, but it's conformally compact. Then in that case, the scale tractor becomes the normal to the boundary. It becomes the normal tractor to the boundary. and so it says that this mean curvature thing coming up has to be orthogonal to the normal tractor, and you unwrap what that means, and it exactly gives you this orthogonality. But you can also handle CMC. And it's interesting what that might mean when it's not codimension 1, but you can mean that the mean curvature has constant length. That's sort of one notion of CMC. And that's exactly the condition that this mean curvature tractor into the scale tractor is constant. So again, a very nice condition. Parallel mean curvature, which is another notion of CMC, if you like. These agree when you're in codimension 1. That means that so usually it means that the mean curvature is parallel according to the canonical connection on the normal bundle, but there's a tractor version which is basically exactly the same. That's what it's saying. So these things then all extend through these conformal singularities that you have in these sorts of situations. So that's what I wanted to say about that. And I mean, more than just saying that these things extend, that all of the stuff gives you the machinery, because the boundary here ends up having a conformal structure. And so if you take a minimal surface like the one I've drawn, say, then the boundary will be a conformal submanifold in the boundary. So you can use these sort of tools I've been talking about to understand that object in the boundary, and then how it extends into the bulk manifold in a smooth way, so everything just extends in that way. Okay, that was it. Thank you. Mm-hmm. Well, it is the L equals 0 equation. Yeah, so it's but the conformal circle equation is the L equals 0 equation for one manifold. So the analog is the L equals 0 equation, but you're now on a manifold, so it's not you can't just solve it as an ODE or something. Yeah. Yep.
So this integral, if degree 1 in U and degree 1 in A.
I think it was, yep.
Yes. That would be some integral for conformal for many. So how does the corresponding integral polynomiality?
Oh, I mean, I wrote it down, so.
Wasn't it good? Yes.
There.
That's,
So.
I can't really read.
So there's the Calignano tensor. There's the. Yeah. So that's your actual tensor. Then. So then it's also polynomial of degree 2 in the.
I mean, which one?
What do you mean by which one?
How many?
Oh, so that's a D minus 1. So that's a tensor with D minus 1 indices. No. So that's just a. This is just first. This just involves one derivative of the. So it's first order. Is that what you mean? Yeah. 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 This N is the analog of the velocity. This is the dual picture, right? So this is the so N is your conormal to your submanifold. Well, it's in a sense it's an analog. It is a submanifold, and you have a conormal object with D minus 1. Actually, D indices I've put here. Sorry, no, D minus 1 indices. What do you, when you altogether, this depends on the 1 jet of K. Yeah. H is the mean curvature. Yeah. It's very similar. Yeah, no, this is very similar. This is the dual, because with the curve, I use the star n, and this is using the n. So it's actually a different thing, but it's very similar. Yeah, so the mean curvature and the n. Yeah.
This is the type of thing. What's called conservation law.
Well, it's simply a first integral, so it has to be constant along.
I'm not talking about PD, right?
Well, it's an object that's has to be constant on that surface, so that in that sense, it's a first integral. So, I mean, you have your favorite way of thinking of what these things mean, but it's a theorem. You know, that is a thing that is then has to be constant along the thing, and this generalizes what people mean by first integrals for curves. It's exactly the same idea, and if you have enough of these, then you would algebraically determine your submanifold. That's what it means. You know, you have a lot of these things that have to be constant. And of course, in the model, you see that that's true, right? Because in the model, you are determining these things by first integrals in a sense, because you have this parallel thing that's a plane, and you have so much information that you algebraically determine your curve. So this is a curved analog of that. Yep. In the model, you always have enough first integrals to determine these things algebraically, right? By definition, because they were determined algebraically as an intersection of planes with a sphere. Just one comment in relation to Armin's question. Of course, when you're not dealing with one manifolds, but distinguished manifolds in higher dimension, these things don't necessarily exist, right? So if you're on a sufficiently curved manifold, it won't necessarily admit a distinguished two manifold or something, submanifold. Yeah. So it's going to imply some curvature vanishing as well, but that's just another story. Yeah. Okay, thank you.